Today we're going to talk about packing. And you can understand packing in a very simple way by thinking of these bubblegum balls. They're spherical and they pack a certain way, and you can see what I mean when I pour them into this container. When I pour them into this container, they fill the container to a certain level. And there's a certain number of bubblegum balls inside of the container. And what I'm going to tell you about works for candy, like the bubblegum, but it works for any particles. It works for sugar. It works for flour. It doesn't matter the size of the particles. It just matters that they're not square in shape, so they don't fill the whole volume. They fill only a fraction of the volume. How much they fill depends on the way they pack. And when you pour them in, they fill a certain volume. They fill a certain fraction of the volume. I can calculate that fraction in a simple way. I can measure the volume of each of these spheres. 4/3 pi times the radius cubed, that's the volume of each sphere. Then I can count the number of spheres and calculate the total volume of the spheres. I can also measure the total volume of the container. And we'll see that the volume of the spheres is less than the total volume of the container. In fact, the fraction of the volume of the spheres over the total volume, that's the fraction of volume that's occupied by spheres. And that's called the volume fraction. And I'll quote that either as a fraction or as a percent of 100. So I know when I take spheres and I gently pour them the way I did with these bubblegum balls, the spheres have to support themselves, and they occupy something like 58 to 60% of the total volume. That's 0.58 to 0.6 is the volume fraction of these spheres. And that's determined, the volume fraction is determined by the fact that each of the spheres must support itself, must be supported by the number of neighbors that it has. They're very disordered, and if I shake them gently, they will actually start to pack better. And if they pack better, their volume fraction increases. So the number per unit volume goes up, and the height of the total number of spheres goes down. They're packing more efficiently, and the volume fraction is increasing. And I know, and this is calculated, that if I have spherical particles like these bubblegum balls, the best I can pack them, if they're disordered, if there's no relationship between the position of one particle and one sphere and the next sphere, then the best I can do is pack them to a volume fraction of 64%. That's called random close packing. That's something that's still debated. We don't know how to calculate that analytically. But every time we measure it, and every time we do a computer simulation, we get the same number, 64%. So spheres pack always to a maximum volume fraction of 64%. That's the best we can do, provided that there's no order in the structure of the spheres. And we can only do that if we shake them until they reach this maximum volume fraction. And that value depends only on the fact that they're spherical. So we'll get exactly the same value if we use tiny spheres or if we use huge spheres. We can only pack them to a volume fraction of 64%. It doesn't matter what the material is. It doesn't matter what the size is. However, if the particles are spherical, like these bubblegum balls, then I can shake them even more. I can shake them very hard, and the volume fraction will increase even further. And the only way it can increase even further is if they order. Each layer forms a flat layer, and they order in a hexagonal order. They order with this hexagonal packing, and the next layer stacks exactly on the first layer. Now they're ordered. They're no longer disordered. They're ordered in a hexagonal packing. And when you do that, and you measure the volume fraction, you see that it's gone up significantly. Instead of 64%, which it was when they were randomly structured, when they're ordered, when they're hexagonally ordered, their volume fraction increases to 74%. And this is not so surprising to you. If you go to a supermarket and you look the way they stack oranges, they'll pack them in this very ordered array, and that's because they can pack them more regularly. It doesn't matter that they're not small like these bubblegum balls. The big spheres will pack just the same way. And if you want to pack them as efficiently as possible, with as high a volume fraction as you can get, you have to pack them in this ordered array. And that's the way to get the largest volume fraction possible. What's interesting about hexagonal packing is that's something that's very easy to calculate exactly. So we can calculate that it's exactly 74%. This is different from the random packing, where we still can't do a perfectly analytic calculation. When they're ordered, we can calculate very simply exactly what the volume fraction is. So far, I've talked about spheres. I've talked about these bubblegum balls, which are absolutely spherical in shape. What happens if the particles aren't spherical? After all, many things are not spherical. For example, here are some M&Ms, and they're not spherical. They're ellipsoidal in shape. How do they pack? What's very interesting is that although we think we understand everything there is about packing, only recently people have measured what the volume fraction of M&Ms are when you pack them. They're very uniform M&Ms, but they're ellipsoidal in shape. They're no longer spherical in shape. So if we measure what their volume fraction is, and we pour them out, again keeping them disordered, and we measure what the volume fraction of these particles is, there's still some space between them, but it turns out the space is greatly reduced. And so M&Ms, ellipsoidal particles, pack much more efficiently than spheres. These pack to a volume fraction of 74%, quite a bit larger than the 64% that spheres packed when they were disordered. And this is something that's only been discovered in the last few years, how things like M&Ms pack. And what's really surprising is that spheres are anomalous. They pack the least densely of any shape. As soon as you move away from spherical particles, they pack much more efficiently. And so M&Ms pack to a much higher volume fraction than do the bubblegum balls. What about other shapes? Many things aren't as uniform as M&Ms or bubblegum balls. For example, what about other candies, like these chocolate chips that Michael likes so much? How do they pack? Let's see. These are much less uniform in shape, and if you look at them, you certainly see that they can pack to much higher volume fraction than do spheres. But exactly what volume fraction they pack to, I don't know. We would have to measure it. If I look at it, I would say that they pack to a higher volume fraction than spheres, but not quite as high as do the M&Ms, because these are not perfectly round or perfectly uniform in shape. The little point prevents them from packing as uniformly as possible. But very generally, different shapes will pack to different volume fractions, and in all cases, if you shake them, you get them to pack more efficiently. You get them to pack more efficiently because they always have to be supported by their neighbors, but they can find configurations where they can fall into a more comfortable position where they pack to a larger amount. It's very difficult to get to a lower volume fraction, so the volume fraction always increases. And you can always see that. If you take marbles, if you take spheres, if you take anything and you shake them, the level goes down, which means the volume fraction increases. So if you want to pack efficiently as possible, you shake them to get a higher volume fraction. That's why Michael, whenever he's making chocolate chip cookies, he shakes them to get as many chocolate chips as he can into the cookies. So far, we've been talking about particles, about candies that have exactly the same size. Each candy has the same size. But many times, the particles come in all different sizes. Well, we can understand that too, just by mixing different sized chocolate chips together. So here I'll pour in a few of the small ones. And if I mix these together, and I mix them enough so that the big ones and the small ones mix, then what I almost always find is that the volume fraction increases. And we can understand that in a very simple way. The big ones have some space between them, and the small ones are so small that they can fit into the smaller spaces. So if I have more and more different sizes of particles, they can pack more and more efficiently. So the volume fraction will always increase when I have particles or candies of different sizes.